Hey guys, welcome to another episode of Genuine Chit-Chat. This week is another Science But Simple episode. The first episode of our mini-series Science But Simple was released, I think it's the 6th episode of the catalogue, so go back and listen to that if you're interested, where we get into a bit more details of why we started it and that sort of thing. And the first episode is about how light bulbs work and a general idea of energy. So the whole idea of this kind of mini-series is just to explain to people sort of things people may notice in life, whether it's household or everyday objects, or things like in this episode where it's the tides and gravity and the moon and the sun and sort of how the sun works, like why it's just this big ball of gas essentially and creating all this heat, like what's actually going on there. And it's incredibly interesting. This whole series is meant to be just explaining things in an easy to digest way for anyone who's interested in science to any degree that they can understand this sort of thing. The episodes will likely be released every 6 weeks or so it's going to be, my usual podcasts normally, and then, every now and then, just one of these Science But Simple will pop up. And if you fancy this sort of thing, check it out. It's not like a funny podcast necessarily, it's definitely more of the informative ones, and out of all the podcasts that I do, it's the least flow sort of orientated. It's not as much like I just have a chat with someone and it kind of veers off into random tangents about a crazy amount of things. It's not quite as natural and organic as that. It's more centered, it's more thought out. We kind of just talk about it before we start recording, figure out what we're going to say. So it's just less than an hour long, trying to talk about things that people may kind of vaguely know how they work but not fully. So that's kind of the point of Science But Simple. I'm going to pretty much stop rambling now, but don't forget to check us out on Facebook, Instagram and Twitter. And just to say, next week's episode will be back to the more usual format. This time it's going to be with my buddy Johnny. It's a two-parter. It's quite a long podcast. I think it's 2 hours and 20 minutes in total. And we go off on so many random tangents and stuff. It's crazy. I need to re-listen to it to try and figure out what I can even name the podcast, because we talk about so much stuff. If you enjoyed the podcast I had with Bradley last week, which I highly recommend, both parts of that I found were hilarious. And I've had quite a lot of positive feedback from people from that as well. So if you want a podcast that's a bit more funny, a bit more chill, a bit more podcast like in a sense, then listen to the episode before this one, or the 2 episodes technically, because I released it in 2 parts before this one with Bradley, and then next week's tune in for the one with Johnny. Anyway, I am actually done rambling now, and before we get started there'll be a quick word from a fellow podcaster, and then we'll get right into it, and I'll talk to you guys at the end.
Hi, this is Tony, the host of the Flix X-Rayed podcast. Each week, I am joined by guests.
Ew.
Hello.
Yo.
Why, hello there.
Hello.
Hey.
Hello.
Hello.
And we have a roundtable discussion where we dig deep and X-ray a bunch of our favorite films, and some really terrible ones too. We really like to go back and take a look at films that may be forgotten, maybe in the past, and still lovable films. If you want, you can follow us on all the major platforms, iTunes, Google, Stitcher.
If you want to find out more, you can find us online at www.flixxrayed.com.
And you can also find us on Twitter, Facebook, and Instagram if you want to reach out to us. Good night, Internet.
Welcome to Genuine Chit-Chat, where we have honest conversations with interesting people. And I'm your host, Mike Burton. And we're back. Another episode of Science Made Simple. We're on the 2nd episode now. Josh is here with me once again.
This is a thing now.
Doing it. We did it once, and now we can keep on doing it. We've got a few more ideas written down. We've got. I'll tell you at the end. I'll probably maybe in the intro or something. I'll talk about all the different ones we're going to do. We just crack straight on into it, Josh. So we talked about this last time. We spoke about how light bulbs worked and just a pretty vague idea about energy.
Yes.
And enthalpy as well. I remember that term. And so now we were talking amongst ourselves before this and thinking like what to do next. And I think we decided on sort of gravity, the moon, how tides work, those sort of things that everyone kind of thinks about. You see the moon all the time. Everyone knows about water and the tides and when the tide comes in. But I don't think a huge amount of people fully understand how it all works. So
if we're going to start with things about the tides, the kind of stuff that people actually see in their day-to-day lives, I want to kind of branch off of that to the moon and the interactions and gravity and how that all works, and probably then tie into some more general solar system stuff with the sun, some light stuff, and we'll just see where it goes. Probably shouldn't take too long for this one, maybe like 45 minutes maybe or so to go
Yeah.
through everything trailing.
Yeah, I mean
Give or
that would be the general aim. We'll just try that, and we'll just see how that goes. Yeah.
Good lesson plans when I'm teaching.
Well, yeah, I mean that's the thing. It's I was just kind of trying to think what we're going to cover. It will just be you obviously blowing out loads and loads of information, and me trying to understand it in my small brain, and then I'll just reciprocate it, I suppose, in a maybe slightly easier to digest format, or just an analogy. Last time I think I did an alright analogy. A couple of people said the whole the current analogy of the people and the friction. It was like, that's a nice one. Now I've got to have to try and do at least one more good analogy, and I'm going to fail terribly. As people who know me, my analogies make no sense to anyone apart from me.
Quota of one good analogy per podcast.
Yeah, that's it. That's what we've got to do. That's what we've got to strive for here. We don't necessarily want everyone to be perfect, but we just give it a go.
Just one. Just one.
Just one. That can be enough. That'll be enough. 40 minutes. See if we can do it.
Right.
So Josh, you want to start us off then? Go on.
So, as most people will probably know, unless obviously you've not really been around like a shore of any kind for an extended period of time.
A lot of mainland folk, farmers and stuff.
Yeah, especially we're the advantage in the UK of basically being a relatively small island, so we're surrounded by water on every side.
We live on the south as well. We live in Southampton.
Yes,
it's the
right
most
on the coast.
Yeah,
which
right
is a
at the bottom.
special case, which I'll talk about.
Oh Christ, already coming in with them tangents.
Tides is basically just where the water levels rise and fall, and it's essentially controlled by the interaction between the water on the planet and the moon, and a little bit of the sun as well, because obviously gravity is all a relative thing. At any given point, gravity is a two-way system where there's pull from both sides. And then basically what happens due to the position of the moon is that there is a bulge in the oceans on either side of the planet. It's slightly offset from where the moon is. It's not like it's completely in line with the moon. It's not what's called tidally locked.
Right.
It's kind of like a drag, almost, like the moon's dragging the oceans around.
What? So is there like a spherical almost indent, or is it a lot more subtle than that?
Well, the idea that the Earth, as you probably know, isn't actually spherical. It's like slightly like squat.
Oh yeah.
It's
not
like
a perfect
that,
sphere. Yeah.
but the oceans then like bulge out a bit more on either side, and that just like flows around as you go, and that provides your tides where that bulge is. There are also two things called spring and neap tides. NEAP, neap.
I've heard the term spring tides.
And that's essentially when the moon and the sun are kind of like lining up almost in certain ways. You have the tides become stronger.
Right.
And so you get more pronounced, like higher tides.
Is that almost
and
like
lower tides.
Thinking about like looking at it? Would that be where like the moon's on one side, then the Earth in the middle, and the sun on the other side? You can almost draw like a line through them. Would that be? When you say line them up, is that what you mean?
I'm not entirely sure on which way. It might be where like, I think it is just where they line up in a certain way. It's a seasonal thing, so it happens like it's almost like a spring, summer, autumn, winters thing. It's like I think it's 4 times a year, sort of.
Yeah, because obviously
it goes between.
The Earth goes around the sun, and obviously.
Actually, no. I can't remember. I have to double check this at some point. I can't remember whether it's a monthly thing, maybe like it alternates around the months, or whether it's a bit more extended.
You're talking of spring tides.
Spring and neap tides. We'll double check that.
Yeah,
but basically, the sun and the moon's gravity basically conglomerate into one larger pull, which means that you have a bigger difference between your high and low tide marks because there's more pull on that bulge. You've got it.
I found it. It says on the internet, a tide just after a new or full moon, when there's the greatest difference between high and low water. So it's when it's the moon cycle.
So when it's a new moon, you have basically no reflection because the moon's basically in line with the sun.
Yeah.
And then the full moon is also in line with the sun, but the other way around. So it's either or when their gravity like combines into a bigger stretch. So and it's monthly. So that's fine.
Yeah.
Oh, well,
this is it occurs twice each month. So
so there we go.
Each state is monthly.
Yeah. So fortnightly. There we go.
Yeah.
So that's how that works. And yeah, it's that bulge. The water's flowing. Again, it's almost like a drag around the planet, as you said. So that then comes to the special case of Southampton.
Well, I was just going to say before you go into that. So is this basically you can go to an area or two areas of the ocean at one time, and if you can go to the centre of where this sort of drag is, would there be no waves there? Is it like the waves kind of are so small they come out from this sort of centre point?
It's nothing to do with waves.
Right.
Waves is stuff that's generated by the bodies of water moving and drag from things like wind and stuff that perpetuate through the ocean. Like, imagine waves are your normal like waves and ripples from wind and stuff.
Yeah.
Tide is like one massive wave that's carrying the entire ocean around the planet as you go.
Oh wow, okay. So
but it's not actually the water moving around the planet, because all the currents and things do that.
Yeah.
It's just like an expansion that follows around.
Right.
So it's the tides going around the planet is not the water actually moving around the planet.
Right.
It's more just a pull by the gravity making the water pool in certain places.
Right.
Because the currents and the things moving from like surface to deep water and things, that has much more of an effect on where any particular body of water is going at any time.
Oh, that makes a lot of sense. So even though there is this big pull on it, because certain waters are so deep, it's not like it affects how much you can actually move. Is that what you mean?
Yeah, like the way that water moves around the planet is dictated more by currents.
Yeah.
The tides is just a bulge in the water levels created by gravity, like meaning that the water kind of like pulls more in certain places.
Yeah, that makes sense. Yeah. So it's not like a huge, gigantic, noticeable thing. It's almost like someone was like pushing on the top of the water, and it's like it just in a certain area, there's more. It's expanding in that way. It's almost just kind of like not where the hand is. It's where the hand pushes it down and everywhere else goes up a bit.
I have an idea.
Yeah.
For your one analogy per thing. Podcast thing. Oh
Lord.
Technical terms. So imagine you're in a sports stadium and people are doing a Mexican wave. Mm-hmm. Each individual, as you move along, is essentially expanding to continue that wave.
Yeah.
But no individual is actually like moving from place to place as that wave perpetuates.
That's a really good way of describing it.
So that's like the tides moving across the planet. It's just that bulge carrying across.
I see. So it's not the whole body, obviously.
The body isn't moving with the tide.
Yeah, the body is the
tide
people.
Is going,
the body's the people, but the tide's almost the hands. It's like the movement of that is. Yeah, that's a really, really good analogy. I like that one.
Well, yeah, we've done it. We're there.
Now let's just go to let's go to ridiculous technical terms that no one can possibly understand. That someone has to like Google every single word. Let's do that. Please don't do that, for Christ.
So the double tides in Southampton, that's the special thing. Double tide. Or double high water, as it's called,
Christ.
Is basically special conditions that are present in the English Channel / the Solent. It's not so much some people. It's a misconception that it's to do with the entrances to the channel, like causing a squeeze on the water in certain ways.
Right.
It's more of a product of friction and the irregular. What's for one technical term which I will explain, bathymetry, which is like the essentially topography but of the ocean floor. That's what bathymetry is.
What's topography?
Like your hills and mountains and stuff.
Oh, so it's like underwater hills and mountains, like sort of a bit obviously down. Like,
so
the shaping of that, and obviously water does not just. When people think about how deep water is, like it does actually hit a bottom. Like there is a point where water stops going down, and obviously if that point is a mile further higher up than another part next to it, then the water in theory kind of in that area would be up slightly more, but because of obviously how water works, it doesn't just shoot up like a rock in the same place.
There's no real like hard differences like that in the English Channel. It is technically all shallow water, like a few 100 meters at most. Deep when you get deep water, that's like over 1 kilometer.
What's that?
1 kilometer down, that's when you get deep water. The Mariana Trench.
I almost said ground.
That's like going for like 10k plus meters. So
that's the one that James Cameron went down, isn't it? In the little.
I have not a clue.
Really?
I know it's basically the deepest point you can go on.
Well, I think he's one of the only people. James Cameron and Mariana Trench found it. There we go. I was subtly trying to say it while googling it. Yeah, the deepest ocean dive. He's gone down further than anyone has in the.
Yeah, they went down it for
He went down
I believe Blue Planet 2 that's recently come out as of this recording as well.
James Cameron went down nearly 11 kilometers, which is 7 miles down to the deepest place of the ocean.
Yep.
Fuck that, man.
I know you have a problem with deep water and water bodies in general where you can't see the bottom. But
I'm just so not cool with. I don't like submarines. I don't like sharks. I love marine life. I want to go scuba diving and stuff, but it's just like deep sea is so terrifying because if something bad happens, you are so screwed.
Yeah, well, we saw at the end of the episode of Blue Planet 2 what happened with their submarine and stuff, and you were like, nope.
We watched that the other night, didn't we? I kept thinking we need to watch some more.
Where the iceberg was like, stuff was scraping off the iceberg and all the rocks were falling and like, not on the thing, but they were like, had a massive rock just fall next to them in their submarine. It's like,
yeah. And they were like, if that had hit the glass, it would easily smashed it. It's like, what?
Yes.
No! Oh my god! Raining ice blocks in the. Anyway, that's good. You guys should go watch Blue Planet 2. It's amazing.
Yeah. So continuing, just basically the resultant combination of the tides moving through the channel with the friction and the irregular bathymetry means that it creates, rather than two what's called oscillations or the swells per day for the tide, it generates it into 4. So you end up with, you get your high water, it dips a bit, then goes high again,
right,
and then goes fully down to the low tide.
Okay. Is that
so
and that's
you
because
double dip into your high tide, basically.
And you're saying that's because of the essentially underwater hills?
Yeah.
Okay. And that's because, that's Southampton. I assume there are other places around that have double tides?
It's a general thing that goes across the English Channel. I'm not sure whether it exists much elsewhere around the world.
Is it because of where the channel goes between France and Spain, and there's
that's
that narrow...
the misconception that like double entrance thing causes it.
I wonder if that is the thing that cuts at the shape of the bathymetry. Is that what you called it?
Yeah, but that's the bathymetry thing is a long-standing like volcanic things and pushing past and stuff. So,
I see. That's more. Is that more tectonic plates, or is that some completely?
Tectonic plates and the gaps between them is where the ocean floor comes from and is generated and destroyed. So but it's the bathymetry is a long-standing thing. It creates that effect, and it may exist in other places. Yeah. This is like the most famous example. Especially we have the Oceanography Centre here and everything. It's well documented and studied and everything.
Very much about boats and the ocean, haven't we? Because we're obviously we're an isolated island. So
yeah, we get a special kind of tide here where we live, which is fun. It doesn't produce any really unusual kind of like side effects in terms of nature and stuff.
It's just like when you want to go out sailing or whatever, you want to get your boat out. It's like, instead of, if it's low tide, it doesn't mean it's such a long time until high tide again. It's a smaller window, but then again, it means that more occasionally it'll be low tide.
Obviously, you do get currents involved with water going in and out with the tide, and that will change with the double tide because the speed of the currents will change and alternate. But so that probably has some kind of effect, but it's not anything that's like hugely, massively impactful. That it makes a really special case out of Southampton. It's just there's a double tide. It's a bit weird. There we go.
Yeah, weirdness. So we'll go. Let's focus a bit more on gravity. I was going to say.
Okay.
If we think about obviously, so the moon and the sun basically end up creating the dents almost. On the top of the water, and then it causes water to move, not dissimilar to the way a Mexican wave sort of moves things across. That sort of idea. So, what is it about Earth? Like, how does gravity work? Because obviously Earth is basically, it's pulling stuff towards it.
Yes.
But obviously, it's not in such a sense that the moon just smashes into the Earth and then stays on Earth and everything nearby Earth starts falling into it. That would be catastrophic. Okay. So what's the sort of, how does it work? Why is it a big thing? Because obviously, if you throw me in space, I won't have a gravitational pull. But you have a certain size thing. What are the circumstances of how they will have their own gravitational pulls?
You have just probably stated one of the biggest misconceptions about gravity.
Here we go. See, this is it. This is why I'm here.
Gravity.
I'm the Alan Davies of this QI.
Gravity is the resultant pull force between two different centres of mass.
Okay.
Which is probably a few big words. Or not so big words, but doesn't mean much unless I explain it. So at any given point, any mass has gravity. So even you throw you into space, or not even into space, just here, sat on the sofa,
Yeah.
talking to us across the table, across the mics.
Yeah.
We both have gravity, and both of our gravity is essentially attracting us to each other in a completely non-sexual way.
Oh, you ruin it being plutonic.
And basically, that force between us is practically nothing.
Yeah. It's more
Which
to
probably
me.
sounds really like...
It's more to me. I'm choking up, actually. I'm literally choking up. It meant more to me, Josh. I don't want to get all emotional on this. The second episode already, we're getting into the romance.
Because our resultant masses is very, very small. Compared to, say, the Earth, the mass of Earth is, compared to a person or an animal or a tree or a rock, incredibly large.
Yeah.
And say you have two bodies of mass that are equal in mass and a certain distance apart.
Yeah.
The center of the gravitational force between them is directly in the middle. If one has much more mass than the other, that center of gravity is pulled much more to that object, so one is pulled towards the other.
I see. Okay.
Which is why when you jump and then you get pulled back down to the ground.
Yeah. Because the Earth is the biggest
yes.
gravitational force.
At a speed, because the accelerator, well, not accounting for wind resistance, because wind resistance and air resistance is an absolute bitch in physics. The Earth's gravitational force, which is measured, gravity will basically be measured almost as, not speed, as acceleration. So have you ever heard that the Earth's gravity, it will accelerate something towards the ground at 9.8 meters per second squared.
Okay.
So if you, in a vacuum, you drop something, it will move 9.8 meters faster per second for every second it falls.
Okay, right.
So if you drop something, it will keep moving towards the ground faster and faster and faster.
So obviously on
and its speed will increase at that rate, assuming that no resistance is involved.
So then there's 1, that's 9.8. Then that's 2, and that's 19.8.
19.6. So
There
yeah,
you go.
that's sort of
Yeah.
like the
And
speed
then
increases
and
that
that's every
much per second.
Right, okay.
Yeah.
And is that like a... With Earth's... with Earth, is that... Like, if you drop certain things off a skyscraper, it doesn't infinitely get faster, and is it like Penny, for example, the misconception?
Technically, it would get infinitely faster,
But
I
incrementally.
believe. But due to wind resistance and all sorts of things, like you end up with what's called a terminal velocity.
Ah, yeah, I've heard that term before.
So that's the maximum speed that something will fall towards the ground
Yeah,
because of the different forces.
Because that's the misconception, is you drop a penny off the Empire State Building, it'll kill someone. It's like, no, it'll probably hurt them a fair amount.
Probably embed it in somebody's forehead, maybe.
Yeah, you could...
Assuming it falls at exactly that angle and someone looks up and goes...
Yeah.
They did that on Mythbusters once. They just like flung a penny and he was like... Looked at it just got went. He was like, I don't know where it's gone. It's just sticking out his head.
Wow.
Dug into his skin on his foot. And he's like, what? He's like, oh!
Yeah, so it's not lethal, it's just a bit of a pain.
Yeah.
I'm getting a cough again.
So that's 9.8 meters per second squared is what's known as Earth's gravitational constant.
Yeah.
And the moon, so let's look at the moon.
Yeah.
The moon and the Earth are pulling each other towards each other at a constant rate.
Yeah.
Then obviously the moon is orbiting, that's the word, I haven't said that word in ages, orbiting the Earth at a speed as well.
Yeah.
And there is the information that's generally somewhere out there, I don't know how many people know this, but the moon is very, very slowly, by like a couple of centimeters per year, moving further and further away from the Earth. Because it is the gravity, the speed that the moon is going around the Earth is more so than the amount that is pulling it towards the Earth, so it's kind of moving away slowly.
Yeah.
It's not going to do that forever. There will come a point because the Earth's spin is also ever so slightly slowing, and it's to do with the gravity and the tides and that bulge pulling the moon back and everything. Eventually, the tides will line up with the moon. The moon will tidally lock with the Earth, and everything will line up, and then everything will basically remain in an equilibrium that doesn't change.
How long do they think till that was going to happen?
We'll never see it. The sun will supernova and engulf us before that point.
Oh man. I want to have that day where it's like the moon can't get any further away. Whee!
At that point, also, you may never see the moon again because it's geographically locked at a certain point on the Earth. So it might be on the opposite side of the planet and never move from that geographical position.
Wait, you mean if it was like over Australia and it locks there, then in theory you'd only be able to see it when you're in that region?
Yes.
What? Really? That's amazing. That's so cool. So one day it would just go click, like click, and then just stay.
It wouldn't be like a ooh, it's going and it stops. It's a very, very gradual process.
I thought it would be very slow, but I just like to
Yeah.
envision someone go, whoa, where's the moon going? What? Oh, it's gone. Down Australia, because that was over, kids.
Yeah, pretty much. It's like when you have what's called a geostationary orbit of a satellite, where the satellite is in an orbit that means that it maintains a position above a certain geographical point on
Is
the
that how they
planet.
make mobile phones work?
Some satellites of that kind will work. That will work in that way because they need to be over the same area of the planet. Yes.
Yeah, okay, cool.
Right,
Right,
but that's essentially because moons. We call ours the moon, but you have I think
sounds quite a
Mars
lot.
has Phobos. You got Titan, Europa, all on the big planets and stuff. They're all moons. What we call moons is a general term. The astronomical term for them is satellites.
Okay.
So when you talk about Earth's satellite or natural satellite, it is the moon.
So it's a satellite is a general term. It's actually just something that's orbiting something. Is that right?
I believe so.
So in theory, is Earth the satellite to the sun?
I think it has to be around a planet.
Oh,
For
okay.
a
So it has to
specific
be
definition.
So it has to be something
Yeah.
smaller than a planet. Right? Okay. That makes
Yeah,
sense.
and then a planet is a body that is orbiting a star.
Yep.
So like you have the asteroid belt, but that's a different thing because it's loads of small pieces in a chain.
Yeah. But so with the sun thing, so explain to everyone so they understand. So the whole thing is the Earth's a certain size, and because of that, it has a certain magnetic field, not magnetic field,
Gravitational
field. Man, I'm terrible. Gravitational pull.
Yeah.
And obviously the moon also has one, and that's what keeps them in orbit. But obviously the sun's one is colossal.
much bigger.
It's like way bigger. It goes past the Earth, past the moon, all the way out to.
Technically, your gravitational pull extends infinitely throughout the universe.
It's just become so micro that it's just
So
incomprehensible.
the best thing you see sometimes from people trying to visually present gravity, if you got a big sheet of circular like elastic or something, and you drop like a heavy marble or something in the middle, and that sheet essentially like bends in on itself, like almost like a cone. It becomes towards that center.
Right.
That bend is the effect of gravity, and then if you pop, like say the little things you pop the coins in that kids used to, and they goes like round and round. And
I
round
love
and
that
round,
shit.
And eventually gets into
you
the
go there all
bottom.
the time. Yeah.
That's essentially like that going round and round and round and round. Imagine that, but it never actually fully gets to the middle.
Right.
Is what something in orbit does.
Yeah.
From gravity. And that orbit, that circular motion, is a special kind of force. Because it's not technically a single force, it's the resultant force of two forces acting in unison. You have gravity pulling one thing towards another, or technically both towards each other to be technical, but obviously one, if it's bigger, will move towards the other rather than the other way around.
Yeah.
And you have the horizontal force, because forces essentially act in straight lines.
Right. What?
Forces, you basically don't, there's no like curve force. There's just any curve or change in direction is the result of a different acceleration or different force being applied.
Wait. So, when you say that, how does that explain like the gravitational pull of the Earth being like around it? Like if it has to be.
Okay, so to dip into a bit of relativity here,
Oh Christ.
not nothing major. So that sheet, have you ever heard of the term space-time?
In films and stuff, and I've seen
Okay.
Interstellar.
Imagine that sheet is space-time, more specifically towards space than time, but space-time.
Okay.
Gravity is that bend in space-time.
Okay.
So gravity is a pull between two masses. Yes, it's a force, but it's not like it's a force of pulling. Like if you pull something towards you, that's moving towards you in one direction.
Right.
So gravity will affect all directions, but the gravitational force interacting between two objects is singular in direction.
Okay.
Okay?
Yeah.
And forces act in straight lines.
Okay.
So to combine those two together, you have one force pulling an object towards another, and one moving perpendicular to that.
Okay. So and that's what makes them orbit, because if you had just one, it would fling it across away from it, and if you had just the other, it would fling it right into it.
Yes.
So you've got one force that is going away. If people visualize it, there's like a ball in front of you, and you put your arms out, like one to the side, like full out straight, and then one dead in front of you. Is that sort of the right idea?
Yeah.
And obviously, if it's going towards almost both, it will go.
Yeah.
It will go past almost. Mm-hmm. It won't go. If you only had one arm out, it would just come straight to your chest. Or if you had the other arm out, it would just go straight past.
Yeah. Let's go for an example. If you have a ball on a rope, or let's go swing ball. Everyone knows swing ball.
I used to love that stuff. Yeah.
Swing ball. Gravity is the string holding the ball to the pole.
Yeah.
The movement of the ball is you're hitting the ball and you're hitting it in a straight line.
Yeah.
But that string is that gravitational pull of the string.
Yeah.
Is holding it to the pole.
Yeah.
So that force of acceleration of motion that you're applying to that ball to go in one direction is being constant, but it also gets redirected.
Well, that makes
So
a lot
that
of sense.
ball is always moving perpendicularly. Perpendicularly. That's a bit of a tongue word. A bit of perpendicularly is a tongue word for dicularly. I'm gonna stop. I'm gonna really stop. That's inappropriate. It's inappropriate. You essentially, that force of motion in the perpendicular is always perpendicular to the gravity, but because of gravity acting on it, that is always changing direction, and gravity is always towards the center.
Yeah, when you think of it, the swing ball thing, that makes it make so much sense. If you just think of the string is literally the gravity, like you hit it, you can hold it up and smack the ball, and your bat can be going in, or racket can be going in one straight line, and it will hit it in a straight line, but the pull of the string will make it curve.
Yes.
And go around it, and that makes so much sense.
And that's how orbits work. Because it's one force acting, a force of motion in one direction, acting with gravity in the perpendicular, and that results in centripetal force, which is essentially the resultant curved force that moves an object around the center of mass.
Yeah. So those two forces put together is the thing that makes it essentially curve.
Yes.
Yeah. Okay. That makes
The opposite, which is the like a pseudo force or centrifugal force, because technically you've got one force that's basically making an object move towards the object.
Yeah.
Centrifugal force, by Newton's law, you should have a force acting in the other direction in equal and opposite to maintain something in stasis. Because it's not technically a force, the opposite of the force that's pulling the object in the other direction to stop it collapsing in on the gravity, doesn't actually exist. But it's known as centrifugal force, but that isn't actually technically a thing. So it's a force that people thought would be there because it's like, oh, this works in one way, so you must have an equal and opposite force going the other way.
Right.
But it's not, because that force doesn't actually exist in the first place. So there's nothing acting in opposite to it.
Okay. Right. Yeah. So the Newton's law thing is obviously you have.
It's a situation where Newton's law of the forces with equals and opposites doesn't apply, because the original force that is quote unquote saying in that law is not a true force in the first place. But the resultant force of two different ones acting with each other. Yeah,
and that's with the Newton's law thing. That's when we were talking about. I can't remember if we mentioned that specifically in the last episode, but
I think we talked about thermodynamics, the last one.
Yeah, but I think
about energy being created and destroyed and only transferred from one form to another.
Yeah,
this is the one about the laws of motion, which is that each action has an equal and opposite reaction.
Yeah.
But in this case, it doesn't apply because there's no action in the first place, because it's the resultant force of other actions combined.
Yeah.
Okay. And that also then applies for the Earth orbiting around the Sun, or our solar system going around the centre of our galaxy, or stuff going around black holes, and all the gravity stuff and things moving around them is all from the horizontal force and the gravity resulting in the curve.
Being hit in a direction, but a bit of string, which is gravity, being attached to a central thing, creating a curve. That swing ball analogy was solid, mate. I like that.
We've got 2 for this one. 2 for the podcast.
I mean, the next one we're going to have to get 3. We're going to have to get 3 for the next one. Or maybe we'll just bank them. We'll just run out of them one day. We'll have to note them down, make sure we've got enough. Okay, so we've spoken about gravity, we've spoken about the moon, we've spoken about how tides work. And we're on about the half an hour mark now. So do we want to get into just a little bit about light and heat from the sun, and then the moon eclipsing it? Do you think you can cover that in about 10 minutes?
Where do you want to start with that?
Well, I'd say we discussed. Oh, actually, is a good one. We didn't talk about radiators before, did we?
I think we did, because about the convection of the heat heating up one area,
Oh,
and
going in
convection
the-
moving it around the room. I believe we talked about that.
We spoke about it another time. That's the thing. And I don't know.
I
if
don't
we
know.
forget. Oh, we don't know about that in podcast. Terrible. But yeah.
Convection does not happen in space. Radiators, the way radiators work, does not work in space.
Okay. Right.
It
So
requires fluid matter to be able to move, to transfer that energy around.
okay.
The energy that we get from the sun is purely through radiation, which is essentially through light.
Yeah.
And it's through mainly heat, is light we basically can't see, which is infrared. Because it's not part of our visible spectrum. There are things that can see infrared, much like there are things that can see ultraviolet. But
We have devices
cannot.
that can obviously.
We have like things that basically read that infrared signal
Yeah.
and then change it into an image, a visual representation for us.
Yeah.
So we can see where there is infrared and where there is not. Like, so we can see relatively high infrared and low infrared to see like difference in heat. So you have thermal cameras and stuff. That's
Yeah.
all they're doing, is changing infrared into the visual and different levels of infrared into the visible spectrum.
Yeah.
So we can tell what has more infrared and what has less.
Yes. That makes sense. Yeah. So so with the sun is it's basically how is it causing all this power? It's loads of gas, isn't it? That's just on fire.
Right, so essentially gas technically on fire, but nothing's actually combusting. Stars
Is this like the
are-
light bulb thing where it's where you've got in the glass?
No.
Oh Christ.
It's so the sun, I'm gonna go back to something I mentioned to you before about plasma.
Oh Christ, yeah.
And plasma is essentially the fourth state of matter.
What are the other three states of matter?
Solid, liquid, gas.
There you go.
So fourth state of matter is plasma. It's difficult to describe. The best analogy I can say is, the sun is a big ball of fire. That is quite literally, it's a big ball of fire. The sun isn't gases on fire.
Yeah.
It's that the gases in the sun are fire.
Yeah.
And a star is basically, eventually, gravity pulls helium. Helium is basically the building block of elements.
Right.
Is the most basic unit of element you can get. One proton, one electron, done. And hydrogen collects in one place, gravity pulls it together, it gets compressed by that gravity, and gravity compresses it, and it builds more and more hydrogen, and that compresses more, and eventually it starts a process called nuclear fusion. So hydrogen atoms start to combine into helium atoms. So you essentially get subatomic particles combining together to create something new.
Right.
And that releases an absolute fuck ton of energy.
Yeah.
Which is basically, and the plasma thing happens because things reach essentially through the temperature and that compression which creates temperature and heat. Because of the whole energy thing of things bumping into each other and transferring energy, that's happening loads and loads and loads and loads as things get compressed. It's not that the hydrogen's like getting so compressed that it's solid, it's still fluid. But it's bumping in, there's so much friction between the particles that they're creating a lot of heat.
So all
And
these
that-
things are basically being compressed into each other, and doing that is causing a reaction.
Yes.
And that reaction.
And it's more than a chemical reaction. It is like atoms fusing together to become something entirely new.
Yeah. And when that happens, the amount of energy that it releases.
Is massive.
And is that what the fire is basically on the sun?
That's all the energy that's being released from the sun, yeah.
Yeah. So that's happening there, and
The plasma that is the sun, and when you have solar flares that release like all that, like the solar wind and stuff, that is essentially like offshoots of plasma being thrown through the.
how
through
are
space.
they kept in this area? Is it their own
It's
weight?
just the gravity that holds everything there.
Yes.
In that pool of reaction.
Yeah.
And that's the thing that people are trying to experiment with to try and create here on Earth
With
to
the,
create fusion reactors, because that is a potentially huge energy source.
Yeah. You
And all you need is hydrogen, which is probably the most abundant element in the universe.
yeah.
Nitrogen, in terms of in the air, we have more nitrogen than anything else. That's just a product of the eventual things. Like, well, let's put it this way: nuclear fusion happens in stars. hydrogen becomes helium, helium becomes something else, and something else, something else. Eventually you get to the heavy metals like iron, and eventually things become so difficult to fuse that the sun runs out of the fuel to keep that nuclear fusion going. It's like a self-sustaining system.
Yeah.
And when that happens, the sun starts to cool down, it expands, the gravity changes, and you end up things going supernova, and the star dies, and it lets all of that matter go.
Mm-hmm.
And that basically then pulls around something else, and new stars take that in, and gravity creates other planets and things. So you and I, from the product of many, many stars' lifetimes, are simply the combined reactions and things that all led up to Stardust becoming a person.
Yeah,
you are Stardust.
I always think it's more amazing because obviously I've said in a previous podcast, which will probably be released now with my buddy Dom. We were just talking about religion and stuff, and I respect people's religious beliefs, but I find personally that it's so much cooler being made from stardust and the billions of crazy things that go on in the universe to create the ridiculousness that is life. And it's like, I find that to be way cooler and more interesting than a dude made me. You know, it's like, that's just my personal opinion, not to get down on anyone in religion. I'm completely fine with it all. It's just, I just think to me that just sounds so cool. You know what I mean?
think God is a non-binary being.
Edgy. Yeah,
I'm not going to get into that. That's probably going to trigger somebody.
Oh yeah, we don't want to trigger people on the science show. But yeah, it's. I just think that's so amazing and cool. So just to clarify with the sun, so I'm envisioning it. So there's all this hydrogen, helium, and
Yes.
hydrogen.
Mainly hydrogen.
Yeah.
Sun is mostly hydrogen, helium, some form of proportion. Can't remember what exactly that
And
proportion
they
is.
hit each other and become another thing.
Yes. Releases loads of energy. Then that continues to combine and combine.
And that keeps combining over and over again, and eventually it runs out of things it can combine into, because obviously
Yes.
it combines to this thing, and then these things combine to this thing, and
Yeah.
eventually you get. as
It
you said,
stops being stable, and you can't create new elements.
Yeah, eventually I almost think of it as this isn't obviously what happens, but almost like it becomes all these things, and then suddenly it just becomes two bricks. Then you hit the bricks together, and it can't do anything, and you're just left with two bricks. And then everything over time becomes that. And then once it's too much for the sun,
Yes.
then when there's too many in a sense almost bricks in the middle, and there's too many of them, then it's just like nope, and it's too much.
Yeah.
And so all the other energy that's still left, that's still reacting and midway through it and isn't quite done yet, is all shoots out, and that's what causes this sort of supernova.
Yes.
Cool.
And then the general point at which a star begins to quote unquote die is when it starts to produce iron as a product of fusion, because that's when you start getting into like heavy metals. The star stops being able to sustain itself.
Does that mean that in the centre of a star there's a small ever-growing size of iron, in theory?
Not, I mean, it's a huge molten ball of temperature, so it's you're not going to have like a lump of iron.
Right.
Like even the core, well, not the core, but like the mantle of this planet that we're on is mostly molten. It's more almost like oobleck, where it's really, really viscous, but it is molten, and that's iron, and that's nowhere close to the temperature of the sun.
Right.
So it would be a very, very much liquid iron.
Oh, okay, yeah.
But I don't think it would be gaseous. I don't think gaseous iron is probably even feasible at any temperature. But it's feasible at some temperature, but it's probably going to combust before then, long before then.
I see. Well, that's cool. And obviously all that energy gets released and it goes through the
So
through
simply
space.
through radiation, release of what is technically photons through light, so you get infrared up to ultraviolet and beyond to like radio waves and gamma rays and stuff. That all eventually is dispersed evenly around the sun.
Yeah.
Obviously, it's going out in all directions.
Yeah.
And a certain amount of that reaches this planet in about 8 minutes, and makes this how we are.
I was just saying, because the sun is 8 minutes behind us, isn't it? It's like
Yeah.
like what we can see. If you look up and look at the sun, I don't recommend that, connect your eyes. But what you see of the sun, if the sun exploded, we wouldn't know for 8 minutes. Well, we would, because we'd have like special.
Yeah, at that point,
If we didn't have NASA, if it was just all these normal people, you just look up.
It's not even that. If the sun starts expanding, it's getting closer to us, and then the distance the light's travelling is less, so we would see it coming, but it's probably just going to expand so quickly that it doesn't even matter anyway. But
if it just disappeared,
Yeah.
if the sun
Like,
just
if
disappeared,
you're
we wouldn't be able to
looking-
see it for 8 minutes. It would not. If somehow some evil scientist made
Yes.
the sun disappear, You wouldn't, if you're just normal people looking around, wouldn't see it disappear for 8 minutes.
Yeah, if you suddenly put like a camera shutter over the front of the sun, like completely covered the sun, the light that had already left the sun would take 8 minutes to get here, and then boop, done.
Yeah, then there'll be a shot.
Yeah. And even looking up at a starry night sky, you're looking into the stars of the past. That light has taken eons to reach us. Like when you talk about a light year, I think another misconception is light year is not a measure of time, it's a measure of distance.
Yeah, it takes 1 year to get somewhere by
yes.
going the speed of light.
Yes.
Yeah, that's just ridiculous to think about. It's like we can't go the speed of light. I can't remember what the percentage is. I think it's like in the 80s or something.
Where things can travel to like the 99.9% of the speed of light. Obviously, things will start to like destruct at that point because of resistances and things.
What's that the problem is humans would be able to sort of
mass
do that sort of thing? Or...
Well, the thing that would, if you're slowly building up to that speed, you're fine because it's things like G-forces and stuff is to do with acceleration.
Yeah.
And it's the change in speed over time that generates the G-forces that potentially could kill someone. Right. If you slowly increase speed as you go, and you're going at the same speed as that object that's increasing in speed, then your like acceleration is very slow, so you don't feel the G-forces, so you can get up to that speed.
Well, getting up to the speed of light would take a long time.
A long time, yes. And then to maintain that takes so much energy, it's not even worth trying.
I see. Well, we won't now because we're now at the 42-minute mark, so we'll wrap this up.
Yeah.
But I think at some point we can go into if we keep doing this, which I hope we do for many months, years, whatever.
This is the thing now. We've done 2.
We can't ever give
up.
There
will be more.
Yeah, till we're like
can't give up
8,
now.
we're like 80 years old, and like science has changed so much, and none of this makes any fucking sense.
Everything I said in episode 1 is now a complete lie.
Yeah, so our understanding of the universe is completely different since we met the squirrel people of Aspen 4. That'd be nice, wouldn't it? Not in our age.
And Ewoks are real.
Oh god, that'd be pretty cute. I'd love to have a little Ewok mouse.
And Jawas, no, they're not. Jawas are Tatooine's not a thing. Mos Eisley is no.
Oh man, but Endor is definitely.
Endor, yes.
But to be honest, it wouldn't be so far fetched. Like if you had other planets with life to have, like you get little bears, so you get like koalas. Like if you got some who somehow became. Like they evolved in a certain way.
Yes.
They actually became that way. But let's not go down that route because
we're ever so slight moment.
Yeah.
Just okay. I have no doubt in my mind at all that there has been life on other planets except from Earth.
Yeah.
The only contention is that I doubt we'll ever be able to encounter something. Because not only does it need to be within a feasible area of space for us to be able to contact, it also needs to have existed within the same time frame.
Yeah.
And our existence, the existence of the human race, not even through like when we have been technologically advanced to basically be in the space age, quote unquote,
it's only like 50 years or so,
is not even a blink in the amount of time that the universe has existed.
Oh god, no. It's literally... What we should do at some point in the future episode is maybe go into the Fermi paradox and stuff and talk about space travel and that sort of stuff a bit more. I think that'd be a really interesting one. So I've got my pen and paper. I'll write that down. Mm-hmm. Yeah, I'll pretend like I'm talking about...
Other intelligent life other than us existed? Almost definitely. Will we encounter it ever? Fuck no. I doubt ever will find intelligent life other than ourselves. Maybe evidence of intelligent life other than themselves, but to actually come face to face with it, I doubt we ever will.
We can discuss this in a future podcast. That's a good subject we'll get on to, because I want to talk about that. I'm in the same boat with you, but we'll talk about more in detail why the reasons we think that. But yeah, so that's pretty much the end of the podcast. Thanks for coming on, Josh. It was a pleasure to pick your brain. We've got, as we said in the next ones, we've got, I was going to say this in the outro, but I'll say it now. We've got, I think, metabolism, eating, life cycles, blood and oxygen, sort of how it works.
So, yeah, we can go into that one.
There's, we were talking about doing potentially, don't hold us all to these, okay? If someone's listened to all these, write them down and thinking we're going to do every one of them definitely.
We're doing them definitely, I'm calling it now.
May change. We're talking about like gadgets, TVs, radios, phones, touch screens and stuff, and maybe get Reese in on that because he's an IT technician.
He's probably much more better than I am, much more better. Oh, grammar.
That's good. You went so well. So well.
That's definitely. He's probably a lot better at that sort of thing than I am.
We'll look it up where you guys come from.
Yes.
Sort of thing. But yeah, then we'll do this one which I've named Crazy Creatures of the Deep and Fave Animals. It sounds like I'm a little girl writing a journal. But we'll talk about like all the sort of, because there's some crazy ass animals out there like mantis, shrimp, and cuttlefish are just crazy, and obviously anglerfish or bioluminescence. But that's just scratching the surface of how cool things are down there. And then also time and how watches work, and also can go into sort of black holes, and what about misconceptions as well. That's
Yep.
what we've got.
That links into something that we mentioned today with gravity and black holes and stuff. So that's probably a nice one to maybe lead on to.
They're all feeding
We'll
into
see.
each other.
We'll see where we go.
We'll have the
what we feel at
network.
the time.
We'll have the network. Yeah. So as always, it was a pleasure to have you on, Josh.
Thank you.
And yeah, we'll see you guys later. And that's the end of another episode. Thanks as always for tuning in, guys. As I said at the start, there is a first episode of Science But Simple, which was episode 6, and that's all about light bulbs and energy and how that sort of works. Last week's episode was with Bradley. It was just a much more humorous, chilled conversation about all matter of things. There's not really anything in particular that we stick to. I think we talk about racism for about 5-10 minutes, and everything else is just random subjects that come and go. But it's a great chat. It's a lot of fun. And next week's release is going to be part 1 of my chat with Johnny, which is a similar sort of vein to Bradley's, just chatting about random stuff. I think we, at some point, obviously I'm really into Star Wars and Johnny's really into football, or if you're American, soccer. And we have not quite a debate, we are kind of just pulling each other's legs, but just kind of mocking each other for liking football and Star Wars and stuff. And it's just a right laugh next week. And then I think the week after that may end up, or the week after that will be the part 2 with Johnny. And then the week after that, I'm not sure which one I'll release. It may be one with John. No one even called John. With Josh again, who's in this episode, and my buddy Reese, who's in the first episode of Genuine Chit-Chat. If you haven't heard it, you should check it out. It's all about whether or not it's ethically right to, in quotes, punch a Nazi, and about political correctness and people using violence to further their own cause and whether or not that's right. So, he's a great guest to always have on. He's a good friend of mine, as is Josh. So they're going to be in one of the future episodes where we discuss sort of transgender issues and whatnot. And I've got a few more podcasts that I'm going to be recording over the next few weeks and stuff, so I'm not really fully sure of the schedule, if I'm being honest with you. I'm just kind of rambling and raving and babbling on about nothing while I'm trying to figure out the schedule, but there isn't really one. So sorry about that, guys. Be sure to follow us on Instagram, Twitter and Facebook. Subscribe on the usual podcast apps and YouTube, and if you feel like it deserves it, give us a review on iTunes, I really appreciate it and it goes a long way. Anyway, thanks as always, guys. I appreciate each and every one of you, and I'll talk to you next week.